Alright, this video is going to be looking at question number 4 of the force introductory questions, and it will also be looking at free body diagrams with the use of frictional force and the idea of F-net and normal force and the interaction between those forces. And so we're going to start off by taking a look at question number 4. So I would suggest that if you haven't looked at question number 4 yet, stop the video, start reading through the question so you have an idea what it's about, and then as you have gone through that, write down all your known and unknown variables, and then start following along with the video, and it will help you figure out kind of the steps involved here. This is quite an involved question. It focuses on kinematics and the idea of Newton's second law and the interaction of net force, frictional force, and applied force. So in this question, ultimately, you're going to be looking at this equation here. And this is looking at the applied force minus the frictional force and looking at the absolute value of that. The goal of this question, and you'll find the goal of many force questions and force friction questions, is you need to figure out 2 of these 3 variables. And once you get the 2 variables, then you're going to be able to find out the 3rd variable. So when you're reading through a question, it's important to interpret what type of force you can establish from the information that's given to you. So in this particular setup, what I've done is I've broken it down into section A and section B. So section A is looking at when the skateboard, there's been an applied force, and it states that it has a constant applied force. It is accelerating through that section. So it's starting off with an initial velocity of 0. It's going to accelerate over a distance of 1 meter for 8.5 seconds. Super slow acceleration, very long time to go for 1 meter, but that is the data that's given to us. And so for section A, we're going to be able to use that information to figure out an acceleration rate, a positive acceleration rate. The other section of the question deals with the skateboard that's coasting. So that is a very important point or concept to pick up from a question. Anytime an object is coasting or sliding to a stop, this means that the only force that's acting on it is going to be the frictional force. So think about, even at the beginning when we talked about the baseball player sliding into second base. When they slide, again, the only thing that's slowing them down is their contact on the dirt. If you think of a box sliding across a lab bench, right, as soon as it's let go, it's going to slide to a stop. Again, the only force that's acting on it is friction. In this case, we got a skateboard. The skateboard's going to be going a certain speed. It's now going to coast for a stop in section B, and it's going to coast for 1.25 meters. And we know that it's going to come to a rest. So we know that final variable is VF. So really from this setup, section A is going to give us a positive acceleration. Section B is going to give us a negative acceleration. Section A, positive acceleration, we're going to ultimately find F-net. In section B, coasting, we're ultimately going to find frictional force. So we're going to figure out frictional force of that equation, and then we're also going to figure out F-net. This will allow us to figure out our overall applied force. So to do this, we're going to go through 6 steps. The first step is, okay, we've got to figure out the acceleration of section A. So again, you're going to treat this as a kinematics problem. We're given the distance, which is 1 meter. We're given the time, which is 8.5. We know the initial velocity of section A is 0. So now we can rearrange that, and then we can now calculate the acceleration of that section. That's a positive acceleration. Because it's a positive acceleration, that really is related to our net force. So this is really an acceleration without friction. Because it's without friction, then we can go to step 2. So we can classify this as F net, no friction. Because there's no friction, then we're going to go through, calculate that. We know that the mass of the skateboard is 0.5 kilograms. We know it now accelerates at a positive 0.0277 meters per second. That's the unrounded number. That's going to allow us to calculate the F net. And so again, this F net is focusing on just the acceleration. This is the force that only causes this acceleration rate. No friction is involved. So this would be Newton's world without any friction. So anytime you take a specific acceleration rate and then multiply it by its specific mass, then we're going to get an F net that represents the acceleration, the force that causes acceleration without friction. This then allows us to go to step 3. And now we're going to find the final velocity of section A. We already know the F net, but now we got to figure out the acceleration rate of section B. So to do that, we got to figure out its initial velocity. And so if we go back to the setup, right, so this is A, this is B. We're going to now calculate the final velocity of A, right? It's moving through, it's going from 0, it's going to accelerate at that 0.0277 meters per second, and it's going to accelerate to a final velocity for section A. Right at that point, we're transitioning to section B. So the reason we want to find the final velocity of section A is now we can figure out or use that information and make it the initial velocity of section B. So we're going to go through this calculation. We're going to find the acceleration. We know the final velocity and the initial velocity. And we're going to be able to substitute that in. Sorry, not the final velocity. We know the initial velocity and the time, rather, sorry. And we're going to be able to figure out the final velocity of section A. So we're finding this point here. Right at that moment, then we can switch over to section B. And so we can use the same number for section B, but then we're going to call it VI of B. Because we can do that, we can now figure out the acceleration rate of section B. And that's what's happening in step 4. Step 4, I am going to rearrange this formula because I know the distance or the displacement of section B, and I know its now initial velocity. That's derived from section A's final velocity. And then I know that my final velocity of section B is going to be 0 because it's coming to a rest. So I'm going to rearrange that formula. So again, my initial velocity here, this is really the VF of A, which turns into the VI of B. So we're going to use that number. We know that the skateboard coasts for 1.25 meters. And so we can rearrange that, and then we're going to figure out the acceleration rate. It is a negative, indicating that it is slowing down. So if we're going to use this in another kinematics question, then we definitely want to keep this negative. However, if we're going to take this acceleration rate and move it into a force equation, so the second law, F equals ma, then we are going to keep it as a positive number, but remembering that it's a negative acceleration, which, remember, this is the area that's coasting to a stop. So the force that's really causing it to slow down is the force of friction. So we can more appropriately calculate the force of friction using this acceleration rate. So that's what step 5 is. We're now going to look at the frictional force, section B. So we have frictional force. That's what we're defining this as. It's still a force. Using Newton's second law to calculate that force, we know that, again, the skateboard is 0.5 kilograms. This is the acceleration rate. So this is the coasting rate, or coming to a rest rate for section B. So the frictional force that's acting on that is 0.011. Now that frictional force is caused by, frictional coefficients, the air resistance, it's the resistance that's found within the wheels themselves. So when we talk about frictional force in the force unit, it's the sum of all the forces. And even if you think of your lab, right, we had the dynamics cart, there'd be friction between the wheels and the surface there. There's going to be friction in the axles of those wheels. There's going to be friction on the string. There's going to be friction in the pulley, friction of the string going over the pulley, right? So when we talk about friction in that scenario, that's all those forces acting together. And it's the same with these questions. When you calculate that frictional force, it's all those frictional forces acting together. Now, after step 5, we now have frictional force, and we also have net force. So this is where we can now figure out our total applied force. So we're going to go back to this equation, which is what I mentioned at the beginning, because we now have our F net, and we now have our frictional force. What we're going to do with this equation is we're going to drop the absolute values, because we're really now just looking at what's the interaction of these forces. So we're going to take that, rewrite the equation without the absolute value. We're going to rearrange it for F net. So we're really bringing our frictional force over to our F net. So it's now going to become positive. And so our applied force is always the sum of our F net, which is our force causing acceleration, and then also the frictional force we have to overcome, which is the same idea and the same setup we had for the giant baby question. In that giant baby question, we had to establish our frictional force, then we had to figure out the acceleration rate, which was our F net, and that allowed us to calculate our overall applied force. Same setup as that, same interaction. So now we're going to take our information, so we know our F net is 0.014, and then we also know our frictional force in section B was indicated at 0.011. So this gives us an overall applied force of 0.025. This means that when the skateboard is being pushed right at the beginning, in order for it to accelerate at that 0.028 meters per second squared, it would also have to incorporate a force or an additional force to overcome the friction that's present with the surface that it's riding on and the friction within the wheels themselves. So in order to actually accelerate that at 0.028 meters per second squared, we need to also add our frictional component. So we would need this total force, and that's what an applied force is. And again, back to your second law lab, that's why the applied force, or the force that was hanging over the pulley, was more appropriately defined as an applied force, or a force of tension, because it was pulling the cart, but that force also had to pull through all those frictional forces. So that's the setup for question 4. You're going to see a number of different types of questions with the same idea. So you definitely want to go through the video, you want to review the video, write down some key components from the video that you have to keep in mind when you look at the questions that you're going to be looking at for your frictional force. Now, in addition to this, you will also be working on some free body diagrams. There's a free body diagram worksheet that you printed off for this class. If you don't have this sheet, the teacher that's looking after the class today will have some extra copies, so you can look at it there. So what you're going to look at for these free body diagrams is you're going to be given some basic information about the diagram itself. So things like mass, the acceleration rate, and possibly frictional force. So we're going to go through a couple examples here. So in this particular question, we want to figure out, okay, what are all the other vectors, or the size of those vectors? So in this first scenario, we know that we have a 0 meter per second. So we're not accelerating. So remember, if I go back to my F net equals FA minus FF, if I look at that interaction, in order for this to be 0, remember that these two quantities have to be the same, right? FA and FF. Well, in this case, I know FF from my diagram, so I know that's 20 newtons. So in order for me to get 0 over here, this also has to be 20 newtons, because I'm really going a constant velocity. So we're going to write over here FA equals 20 newtons. Now, we have some other vectors that we need to be concerned with. So we need to figure out our force of gravity, right? So force of gravity is going to be looking at mass times acceleration. So we know that the force of gravity is going to equal 8 times 9.8. Now that will come to 78.4, but we're just going to round that to 78 for the purpose of this example. So that's 78 newtons. Now, we know that this is going to be on a horizontal surface, so unless it's indicating that it's moving up and down, we're going to assume that our force of gravity is equal to our normal force, which I'm just going to erase some of this stuff here. And we know that the normal force is equal to our gravitational force, so that's also going to be 78 newtons. Now, so that's one type of example. So I'm going to show you another example that you will also come across. You're going to get an example that will have now an acceleration rate, and then you will also get one with an actual frictional coefficient. So in this case, we got to figure out some information here in order to use our frictional coefficient. Now, if you go back to that friction video, you would know that normal force is a key component to that frictional or coefficient of friction equation. So we're going to figure out our normal force. The way we figure out our normal force is we're going to figure out our force of gravity. So it's going to be mass times acceleration. So we know that we have 12, and that's going to be multiplied by 9.8. So that's going to equal 118 newtons. Again, I've just rounded that answer. We're not moving up and down, so that's going to be the same. So 118 newtons. Now, the next key component is now figuring out, okay, what in the world is our frictional force? So now this is where we're going to use our frictional coefficient. So we know that in a frictional coefficient, we got frictional, this is going to be kinetic friction, moving friction. So we know that we have kinetic friction, so moving friction, or force of kinetic friction, over our normal force. So we're going to rearrange that because we really want to know what the force is of kinetic friction is. And so we're going to take then the 0.4, multiply it by our normal force. And again, just for the purpose of the example, I'm just using rounded numbers. And so the kinetic friction, which is really frictional force, is going to be, after calculating it, it's going to be 47 newtons rounded. So we can now go up here, and now we know our frictional force is equal to 47 newtons. Now, this situation is a little bit different because we got our frictional force. We do not have a constant velocity because we have an acceleration rate. So we need now to figure out our F net, the force is going to cause an acceleration, and then also add our frictional force to it to figure out our overall applied force. So we're going to take a look at that. So our F, let me just move in a different location here. So our F net is going to equal mass times acceleration. So we know the mass here is 12 kilograms, and then we're going to multiply that by 3. So I'm just going to slide over here. So that's actually going to equal 36 newtons. Now remember, we're kind of going all over the place here, but remember that applied force is equal to your F net plus FF. So we're going to take our 36 and we are then going to add that to our frictional force, which is 47. So this means that we are going to have an applied force of 83 newtons. And again, if you look at the overall, again, you have to think through what the interaction of the forces are showing us. So again, if you look at this, our applied force, again, is always the combination of our net force and frictional force. So we calculated our F net using our acceleration rate and our mass. That gave us 36 newtons. We calculated our frictional force by using our frictional coefficient and our normal force. And so that calculation's here, so that equaled your 47 newtons. It's the sum of those, and that's why we came to 83. So there should be a difference between those numbers because there is an acceleration rate. The normal force and the gravitational force, there's no indication that it is moving up and down. So again, we can assume that that normal force and the gravitational force, so this should also have newtons on there, should be the same. So that's the other worksheet you're going to work on. So you really have two items that you're going to work on. You have your frictional force worksheet, which is based primarily on the first video on frictional coefficients. If you haven't seen that video yet, you need to go back and take a look at that, take notes on it, so you can actually complete the worksheet. Once you've done that, you've gone through that worksheet, then you can move on to your free body diagram worksheet. And again, you can use these as an example. These two questions I've gone through to help you work through that worksheet. In addition to that, if you have not completed the introductory force questions without the idea of coefficients, you need to go back and complete those as well. Take a look at that skateboard question again, one I went through on this video, and again you want to go through, assess where your understanding lies, right? What do you understand about the question? And if there's areas that you're still not clear about, then you need to come in for some extra help, or today's class is a good day to work with a partner, kind of work through those questions. On Monday's class, we will continue on looking at this. We'll take up these questions, and we'll continue to look at the idea of frictional coefficients and different types of word problems. All right, good luck, and we will see you on Monday.